Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Hasif, and for my first part, I would like to talk about the introduction on digital signal processing windowing filters for the subject BERT 3373, which is digital signal processing. And our lecturer's name is Puan Isadora binti Mustafa. So, for the first part, allow me to introduce our group member, which consists of 5 people, including myself. And so, uh, what are windowing filters? Windowing filters transform ideal infinite impulse response into practical finite one. So, uh, in simpler terms, windowing filters are methods used to take an ideal filter response which is often infinite and make it finite so that it can be implemented in real world application. So moving on the second point, windowing filters shape the filter's frequency response. By applying a windowing function, we can modify the impulse response of a filter to achieve specific characteristics, like reducing unwanted oscillation or managing trade-offs between side lobe suppression and frequency resolution. Moving on the last point for windowing filters. For example, the filters that we chose is Hamming windows and rectangular windows, which are two different approaches to truncating the impulse response, and they offer distinct advantages depending on the application. So, moving on the third slide, why the importance of windowing filters? So, why are windowing filters so important? When designing filters, especially finite impulse response, which is FIR filters, we often need to balance between frequency resolution and side lobe suppression. So, windowing filters also helps us shape the filter's frequency response to minimize artifacts like ringing effect, which occur when there are abrupt truncation in the impulse response. Lastly, they are also used in applications like signal smoothing and spectral analysis, making them a important and versatile tool in digital signal processing. So moving on to our last slide, which is objective. Um, First, we aim to demonstrate the characteristic of difference between with difference of different filters which we chose, which is Hamming and rectangular windows, explaining their unique properties and trade-offs. Second, we will organize the technical content step by step to show how these filters are designed and analyzed using MATLAB. Lastly, we will showcase how our team collaborated to present meaningful and interesting content about windowing filters in digital signal processing. So, with that, let's move on to the next person to explain the theory and characteristic of both windowing filters that we chose. That is all for me. Thank you.
Assalamualaikum dan salam sejahtera. Saya Muhamad Safuan. Jadi hari ini saya akan bercakap tentang teori dan karakteristik kepada filter yang diberi nama Hamming window. Okey, jadi apa itu Hamming window? Jadi Hamming window ni merupakan salah satu tertingkap ataupun window yang digunakan secara meluas dalam dunia signal processing. Jadi Hamming window ni dia membantu kita untuk mengurangkan ataupun menyelesaikan masalah yang biasa terjadi lah. Seperti masalah tersebut yang dipanggil frequency leakage. Okey. Jadi macam mana frequency leakage ni terjadi? Frequency leakage ni terjadi apabila satu tenaga daripada satu frekuensi dia termasuk ataupun tercampur di dalam frekuensi yang lain yang menyebabkan kita punya keputusan analisis yang kita dapat tu tak cantik lah ataupun kurang baik. Okey, jadi terdapat dua jenis lobus ataupun type of lobe di dalam Hamming window ni. Jadi lobe yang pertama merupakan wide main lobe. Okey, untuk wide main lobe ni apa benda dia? Okey, wide main lobe ni merupakan dia mewakili kepada resolusi frekuensi. Okey, walaupun wide main loop ni dia terhasil lagi besar daripada tertingkap yang lain seperti rectangular window. Jadi, tapi kompromi dalam resolusi yang terjadi dalam hemi window ni adalah sangat minimum dan digunakan untuk kebanyakan aplikasi seharian lah. Jadi yang kedua adalah apa itu low side lobes. Okey, low side lobes dia merupakan lobe yang berada di sebelah wide main lobe. Jadi low side lobe ni sangat ditekan ataupun kita perlu mengurangkan dia dalam jumlah sekitar lebih kurang 41 desibel di bawah wide main lobe. Jadi side lobe ni mewakili kepada komponen frekuensi yang kita tak nak lah. Maknanya yang berada kat tepi tu kita tekan dia sebab kita tak nak. Jadi dengan menekannya adalah sangat penting untuk kita mengurangkan kebocoran frekuensi daripada berlaku lah kepada frekuensi yang lain. Okey, kat sini saya boleh tunjuk ini adalah wide main lobe kita dan sini adalah low side lobes kita. Jadi kat sini hemi window ni dia terjadi daripada kosong, kemudian dia akan naik sehingga ke puncak dia, ke puncak maksimum dia, kemudian dia akan turun pada kosong. Jadi ini adalah gangguan frekuensi ataupun kebocoran frekuensi yang kita tekan di bawah wide main lobe ni. Ini bentuk yang terhasil lah di atas ni. Okey, seperti yang kita dapat lihat, bentuk dia adalah sangat simetri. Jadi macam saya cakap lah, bermula dengan kosong dan berakhir dengan kosong. Okey, jadi di dalam domain masa ni, hemming window ni dia mengecilkan tepi isyarat kepada kosong dengan lancar. Jadi dia dapat menghalang peralihan yang mendadak lah. Maknanya ada gangguan frekuensi yang mendadak yang boleh membawa kepada artifak yang tidak kita ingini dalam domain frekuensi. Okey, kita akan beralih kepada mathematical formula ataupun mathematical method. Jadi formula ini adalah formulanya, iaitu W N sama dengan 0.54 tolak dengan 0.46 cos kurungan N besar tolak 12 pi N dan kurungan. Okey. Jadi apa benda formula ni boleh tolong kita? Okey, formula ni membantu mengecilkan tepi isyarat tadi yang saya tunjukkan, iaitu low side lobes tu dengan lancar kepada sifar. Jadi kemudian window jadi tu berbentuk loceng. Okey. So dengan tirus yang licin ni dapat mengurangkan ketidakselanjaran tajam yang sebaliknya akan memperkenalkan artifak yang penting dalam sesebuah domain frekuensi. Okey, jadi formula ni macam mana kita nak gunakan dia? Okey, untuk mengiranya, andai kata dia beri N, N ini mewakili kepada integer iaitu 5 dan N kecil pula mewakili kepada jumlah nombor iaitu kesemua nombor yang berada di dalam 5 ini. Jadi jika N besar kita adalah 5, maka N kecil kita akan menjadi 0, 1, 2, 3 dan 4. Okey, macam mana kita nak gunakan formula ni dengan parameter yang diberi ni? Okey, sebagai contoh, ini saya bagi satu contoh mana saya akan kirakan kosong yang pertama ini. Jadi untuk N sama dengan kosong, dia akan jadi, kita gantikan N ni, kita gantikan kepada kosong. Dia akan jadi W untuk kosong, dia akan jadi sama dengan 0.54 tolak 0.46 cos kurungan 2 pi darab kosong per 4 tutup kurungan. Okey, jadi jumlah ataupun keputusan yang kita akan dapat adalah 0.08. Okey, kemudian kita perlu gantikan N ni kepada nombor-nombor yang seterusnya seperti 1, 2, 3 dan 4. Okey, jadi ini merupakan value yang saya dapat daripada pengiraan daripada 0, 1, 2, 3, 4. Kemudian dia akan menjadi W sama dengan 0.08 untuk 0, 0.217 untuk 1, 0.54 untuk 2, 0.863 untuk 3 dan 1/0 untuk 4. Okey, jadi sebagai kesimpulannya, Hemming window ni sangat sesuai lah untuk aplikasi seharian kita dalam signal processing seperti pemprosesan pertuturan ataupun kita menganalisis signal audio di mana ia membantu mengecilkan ataupun meminimumkan sedikit sebanyak gangguan frekuensi daripada frekuensi yang lain, mana kita panggil frekuensi leakage. Okey, saya rasa itu saja daripada saya. Saya akan serahkan kepada rakan setugas saya iaitu Muhammad Irsyad. Terima kasih.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irsyad, and so I'm going to be continuing my part for the rectangular window filter. So it is generally known to be the most common and the simplest windows, and usually the most straightforward one. It is used usually to analyze finite segments of signals. Okay, so based on the screen that you can see right now. Okay, this is the IRF graph. Can be broken down into the main lobe and usually the side lobe. So the main lobe is the bigger part, the bigger slope, okay, of the graph. Okay, and then we can continue to the next part where it can be explained or broken down into formula. Okay, so this is the formula where omega n is equals to bracket 1 0, okay, and 0 is lesser than or equals to n, or lesser than equals to capital N minus 1, where n is the total length of the window. Okay, so it takes segments of signals without tapering. So basically it is a simple function that takes a segment out of a signal without tapering, without any tapering. Okay, and it multiplies. Okay, so basically it multiplies the signal with a box shaped function, as you can see on the screen right now. Okay, and it usually selects segments without applying any weighting or tapering to the edges. Okay, so now we move on to the frequency domain analysis. Okay, so this is the graph for the main lobe and the side lobe for the rectangular window with values. Okay, the same formula can be seen and used in this picture right here, in this formula. Okay, so where omega n is equals to 1 0, for n equals to 0.1, and continue on to the value minus 1. Okay, so how does the window impacts frequent domain? Okay, so basically it impacts it in a way where the Fourier transform of the rectangular window is a sinc function. Okay, so next is the key features of a frequency response. So the graph here shows the sinc function of a frequency response of a rectangular window. Okay, where the values given here, okay, amplitude and the frequency, and the main lobe here being the biggest thing that we can point out here, and the side lobes on the sides. Okay, so there are two main features, two main things that we can usually describe, or we can usually talk about when pointing out a rectangular window function, rectangular window window filter. Okay, where a rectangular window filter has narrow main lobe. Okay, so if you can see here on the graph, this is the main lobe, where it is shaped, where it's not wide. Okay, it is not wide, it is narrow. Okay, in this shape right here. Okay, so it's narrow compared to the side lobes that is large. Okay, so what is the characteristics of a narrow main lobe? So basically the central peak, okay, the central peak function is narrow, as you can see here. The very tippy top is narrow, and it ensures a good frequency resolution. Okay, yes, as you can see here, it ensures a good frequency resolution, and it meaning that it has the ability to distinguish closely spaced frequencies. Okay, So that is for narrow main lobe. The other part, the other characteristic is that it has or it possesses a large side lobe. Okay, so in this, what does it mean? So it's prominent. Prominent means it is high in altitude and it causes spectral leakage. Okay, so when spectral leakage is caused, it will spread energy into adjacent frequencies, and yeah, it will spread adjacent frequencies, energy into adjacent frequencies. Okay, so yeah, based on the graph that we can see here, okay, this is the central peak of the main lobe, and it's it is narrow. Okay, and there's the side lobe. So if you compare it to other windows such as the ham or the hen frequency response, windows, they tend to have a large main lobe. Okay, but they have narrow side lobe, so there's a difference in that term. Okay, so from that we can make a sort of a conclusion or a relationship between the size of the main lobe and the size of the side lobe, where a narrow main lobe, okay, it will provide a better frequency resolution. Okay, where a high side lobe, okay, it will provide a poor suppression of spectral leakage, like I mentioned earlier. Okay, spectral leakage, where energy will be expressed into adjacent frequencies. Okay, so yeah, that is basically my part for rectangular window filter, and we will move on to the next part. Thank you very much.
Assalamualaikum and salam sejahtera. My name is Muhamad and Iskandar bin Gaffar. Today I'm going to explain on how to design uh, design design window filter. First is rectangular. So the first is parameters n equals to 10. This set the length of the filter to 10, and then FC equals to 0.25. This is the normalized cutoff frequency, which is a fraction of the Nyquist frequency. And then center equals to n minus 1 divided by 2. This calculate the center index of the filter, which is used to determine the center of the impulse response. So second one is initialize the ideal impulse response array. So an array H ideal of zeros is initialized to store the ideal impulse response, and then calculate the ideal impulse response. A loop iterates over the range of 1 to n for each index. If n is the center index, the center value of the impulse response is calculated as 1 minus 2 times frequency cutoff. And then for all other indices, the ideal impulse response is calculated using the sine function, which is sine 2 times pi times f frequency cutoff n minus center minus 1 divided by pi times n minus center minus 1, which is modified for high pass filtering. And then window application. First, a rectangular window is defined as an array of 1 W rectangular, meaning no modification is applied to the impulse response. And then the high pass filter impulse response is calculated by multiplying the ideal impulse response by the rectangular window, and display the result. First is ideal impulse response, rectangular window, and high pass response. These windows are displayed in the command window, which is like this. This is the result, and then plot the result. So the plotting has three plot, meaning which is ideal impulse response, rectangular window, and high pass filter response. So this is the result, and ideal impulse response. This will show the theoretical response of a high pass filter, which typically has a central peak and decays toward the edges. And then rectangular window. This will be a flat line at 1, indicating that the rectangular window does not alter the impulse response. And then high pass filter response. This will be the same as the ideal impulse response, since the rectangular window does not modify it. And that's it for rectangular window. Hello, so the next one is Hamming window. So it is the same as rectangular. The parameters n equals to 10, the length of the filter is 10, and fc equals to 0.25, which is a fraction of the normalized cutoff frequency. And then center equals to n minus 1 divided by 2 is this calculate the center index of the filter, which is to determine center of the impulse response. And then the calculation of the ideal impulse response is the same as rectangular, which is an array ideal of 0 is initialized to store ideal impulse response. A loop and over the range of from 1 to n for each index. If n is the center index, the value of the impulse response is calculated as 1 minus 2 times fc. And then for all indices, the ideal impulse response is calculated using the sine function, which is sine 2 times pi times fc times n minus center minus 1 divided by pi times n minus center minus 1. So this is the difference between the rectangular and Hamming, the apply of the Hamming window. So for the Hamming window is defined using the formula 0.54 minus 0.46 times cos 2 times pi times 0 n minus 1 divided by n minus 1. And then calculate the high pass filter response, pass impulse filter, high pass filter impulse response, which is this window is applied to the ideal impulse response to create high pass response, which is H ideal times W Hamming. And then we run this, we get the display result, which is ideal impulse response, Hamming window, and high pass filter. This will show in command window, which is this. This is the result for Hamming. And then the plot will plot the result. It has three subplot, which is ideal impulse response, Hamming window, and high pass filter response. This is the subplot. So ideal impulse response, this plot will show theoretical response of the high-pass filter, which typically has center peak and decays toward the edges, and then Hamming window. This plot will show the Hamming window, which is a smooth curve that starts and ends at zero, peaking in the middle. The Hamming window reduces the side lobes compared to a rectangular window, which helps in reducing spectral leakage. And then high-pass filter response Hamming. This plot shows the modified impulse response after applying the Hamming window. The response will be smoother compared to the rectangular window case, and the side lobes will be reduced due to the windowing effect. That's it for Hamming window. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Muhamad Huzaifi bin Yusri. So, saya akan menerangkan berkaitan dengan aplikasi FIR filter bagi Hamming Windows dan Rectangular Windows. So, kami menggunakan audio untuk membuat aplikasi bagi kedua-dua FIR filter ini. So, ini adalah kod untuk Hamming Windows yang mana pada awalnya kami gunakan function audio read untuk membaca audio yang kami gunakan, iaitu 20,000 wave. So, untuk audio ini, number of sample dia adalah 20 Hz and sample rate dia adalah 20,000 Hz juga, disebabkan duration untuk audio ini adalah 1 second. So, daripada audio tersebut, kita convertkan dia kepada mono, disebabkan audio ini adalah stereo. So, kita convertkan dia kepada mono untuk kita mergekan dalam satu signal sahaja. So, next, kita define dia punya filter parameter, iaitu filter order dia adalah 101 and cut off frequency dia adalah 5,000. So, untuk Hamming Windows, kami menggunakan low pass filter yang mana nilai bawah daripada 5,000 Hz akan diambil kira. So, selepas itu kita design FIR filter menggunakan function FIR1 Hamming Windows. So, dia punya N adalah filter order, iaitu dia punya coefficient. And next is dia punya WN, which is dia punya frequency constraint, dia punya skala. Dia gunakan dia punya cut off frequency bahagikan dengan sample rate bagi 2. So, cut off frequency adalah 5,000 dan sample rate adalah 20 kHz. Kita bahagikan dia 2 disebabkan audio ini adalah stereo. So, disebabkan kita mono, so kita bahagikan dia kepada 2. Lepas itu kita define dia punya F-type, iaitu kita gunakan low pass filter dan type untuk filter ini adalah Hamming. So, kita apply dia ke dalam audio signal menggunakan function filter. Kita masukkan dia punya numerator, iaitu Hamming filter. Denominator dia adalah 1 and dia punya input data adalah audio data. So, next kita keluarkan dia punya frequency response of filter. Kita menggunakan function fix, iaitu FRQZ. Masukkan Hamming filter. Lepas tu dia punya numerator and denominator. Lepas tu dia punya input data, iaitu sample rate. Seterusnya kita keluarkan juga frekuensi untuk original signal bagi audio tersebut. Sama juga lepas tu kita masukkan output data, dia punya numerator, denominator and dia punya input signal. Input data. So, selepas itu kita plotkan dia kepada dua bahagian, iaitu untuk time domain dan frequency response. So, result yang kita dapat adalah macam ni. So, ini adalah result untuk data sebelum difilterkan Dan setelah difilterkan, yang ini adalah result dia lah. So kita boleh nampak memang humming Windows kurangkan ripple untuk reduce leakage signal. So original audio, dia punya peak data dia adalah 20,000, iaitu dia punya sampel data. So bila dia difilterkan, dia punya peak adalah 4371.24 Hz. So next is the rectangular. Function sama, kami menggunakan audio yang sama, iaitu 20,000.wave. Cuma kami tukarkan pada bahagian design. Dan design, apply filter dan frequency response. Dapatkan nilai filter bagi rectangular window. So result yang kami dapat adalah untuk result bagi rectangular window terdapat ripple, yang mana kita dapat lihatlah kebocoran yang berlaku pada apabila menggunakan rectangular windows ini. So untuk perbezaan antara kedua ini, kita masukkan dalam satu kod dan kita dapat lihat Windows dapat mengurangkan ripple, tetapi rectangular Windows tidak dapat mengurangkan ripple. So untuk main loop pula, Windows mendapat main loop yang kecil berbanding dengan rectangular window yang mendapat main loop yang lebih besar. So apabila main loop lebih besar, rectangular window dia akan menyeimbangkan lagi signal tersebut. Tapi kalau main loop kecil, dia lebih tajamkan lagi frekuensi tersebut. So daripada sini juga kita dapat lihat dia punya side loop, yang mana humming window dapat mengurangkan side loop dan untuk rectangular tidak dapat mengurangkan side loop. Jadi itu saja daripada saya. Sekian, terima kasih.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So my second part is I would like to explain on how to calculate the impulse response of an FIR filter using rectangular window and humming window. So firstly, we use both of these formula for each window, which means that for finding Hn equals to HDN times omega n. So for finding HDN, we use this formula for when n is not equals to m minus 1 per 2. The bottom formula is for n equals to m minus 1 per 2. So after we know on how to use both of these formula, this is the calculation that we got. So for rectangular window, to find omega n for rectangular window is always 1. So to find Hn, which is HDN times omega n, so 0.06366 times 1, which will get the same amount as HDN. So we repeat the steps. We repeat the steps until n is 10. So for Hamming window, the formula for omega n is 0.54 minus 0.46 times cos 2 pi n per m minus 1. So for example, for n equals to 0, the HDN for N0 is 0.06366 and the omega N is 0 0.08000. So which will get 0.00509. And we will repeat the steps until n equals to 10. So that is all from me for the calculation part. Thank you.